All right, let's dive right into a really fascinating and kind of out there model of spacetime called the MMU. We're going to see how just three core ideas, compression, stiffness, and time being a projection, can paint a very, very different picture of our reality.
So, let's just kick things off with a wild idea. What if the vacuum of space isn't a vacuum at all? What if it's actually a dense, elastic grid made of countless microscopic, vibrating engines, and everything we see and experience is just a shadow of what they're doing in the background? Well, that's the core idea we're exploring today.
Okay, so where do we even start with that? To really get our heads around the MMU framework, we've got to begin with its most fundamental piece, its basic building block.
And here it is. This little thing is called the cell. I want you to think of it like the ultimate cosmic Lego brick. In this model, all of spacetime is imagined as this huge interconnected lattice of these dual-tetrahedral elastic structures. Everything is built from this one single geometric unit.
Now, this isn't just some static block. Nope. Each your cell is like a tiny engine, and it has three hidden ways it can, vibrate or respond. As you can see, they're called modes: an electric mode, a torsional or magnetic one, and a volumetric or gravitational mode. This is the hidden machinery.
And this right here, this is the golden rule of the entire framework. It's super important. We can never see those hidden W2, W3, and W4 vibrations directly. The only physics we can ever measure, everything from light to gravity, is just a projection, like a shadow, of all that hidden activity onto a single observable axis we call W1. Okay, so we've got the basic blueprint. Now let's look at what makes this whole thing run, and it all comes down to one concept: compression.
The state of any one of these R cells is all about its local scale, which we're calling A. You could just think of it as its size, right? If A shrinks, the cell's being squeezed. If it gets bigger, it's expanding. Simple as that. But this one little variable, it changes everything. So how does the cell react when you squeeze it? Well, that's where the simple but incredibly powerful stiffness law comes in. Basically, stiffness, we'll call it K, is proportional to the inverse cube of its size A. Let me put that in plain English. The smaller you squeeze it, the exponentially stiffer it gets, like way, way stiffer. This law sets up a direct chain reaction that's basically the engine for this whole model. So follow me here. You compress an cell, making A smaller. That causes its internal stiffness to just skyrocket. And what happens when something gets stiffer? It vibrates faster, so its hidden modes start oscillating like crazy. And that faster internal vibration, well, that just means it has a higher state of hidden energy. See the chain? Compression leads directly to more hidden energy. Now we're getting to the really mind-bending part of all this. If squeezing spacetime makes its hidden engines vibrate faster, what on earth does that do to how we experience time?
The answer is probably not what you'd expect. You might think faster vibrations, more time passes, right? That feels intuitive. But nope. In this model, it can actually mean the complete opposite.
And here's why. In the MMU, time isn't this fundamental river that just flows on its own. Just like everything else we observe, time is an emergent property. It's a specific kind of shadow, It's a particular combination of all that hidden W2, W3, and W4 activity, projected onto that one axis we can actually see, W1.
And this gives us a totally fresh take on something we already know about, like gravitational time dilation. The standard view is that mass warps spacetime, and that's what slows down time. Well, the MMU says something different. It says mass compresses the cells of spacetime. This cranks up their hidden energy, sure, but it actually shrinks the amount of that activity that gets projected out as observable time. So the clock ticks slower, not because space is warped, but because its time shadow is getting smaller. Kind of cool, right?
So now that we have this little toolkit, compression, stiffness, projection, we can start to see how the MMU defines the different laws of physics that we see all around us. It calls them regimes.
So what's a regime? It's just a special case where the stiffness of different hidden channels match up. For example, when the electric stiffness and the torsional stiffness become equal, bam, you get the Maxwell regime. That's the physics of light. Or when electric stiffness matches gravitational stiffness, you get the right conditions for something like a proton-neutron transition. It's like different laws of physics are just different resonance points in this underlying cosmic machine.
So, what happens if we take this whole idea of compression and just push it to the absolute limit, to its breaking point?
Well, that breaking point is called the Planck limit. It's the ultimate state of compression.
The Earth cell gets squeezed so hard that it becomes insanely stiff, and all three of its internal stiffness channels, the electric, the magnetic, and the gravitational ones, they all become equal. The whole system just equalizes. It reaches what's called total degeneracy.
And when that happens, when you hit full degeneracy, well, the consequences are profound. With all the stiffnesses being the same, there's no preferred internal direction anymore. Those delicate balances that create stable particles, they can't hold, and you can't get a clear projection of time or energy or mass anymore. Basically, physics as we know it just dissolves. So the central claim of the MMRU really is this. As spacetime gets compressed, its hidden structure becomes stiffer, faster, and more energetic. And these special conditions, where stiffnesses become equal, they create the distinct regimes of physics that we know. But at that ultimate limit of compression, the system becomes fully degenerate, and the very structure that allows for a distinct, observable universe just ceases to exist. Which leaves us with a pretty deep question. If the structure of physics breaks down at the Planck limit, what does that imply about the nature of reality itself?